we are ready for step 2, which is embedding the integers into x and y. This is a very cool, weird, thought-provoking part of the proof because we've made the natural numbers and now we have to figure out a way to make the integers from the natural numbers. And the way we're going to do it is very interesting. You might think that the way to do it is just to say that for every number 1, there's a -1, for 2, there's a -2, and so on. And that might work, but then when we're dealing with addition and subtraction and multiplication, we would have to deal with each combination individually. We'd have to do, plus and plus. What's it mean when you're adding two positive numbers? And then what's it mean when you're adding a positive and a negative and a negative and a negative, and so on. And it could get quite tedious. So instead, we're going to do it in a different way. And this is also interesting because it yet again emphasizes the similarity and the relationship between integers and rational numbers. So what we're going to do is construct the integers as equivalence classes of pairs of natural numbers with a and b elements of the naturals. And so we'll think of a and a comma b as representing the number a minus b. So then if a is larger than b, so if it's like 3, 2, that would equal 1, right? And then maybe 2, 4 would equal -2 because it would be 2 minus 4. So in this way, we can represent all of the integers. But the important thing to remember is that actually, we can't actually do 2 minus 4 in the natural numbers because the answer doesn't exist. It's not a natural number. So we're not actually defining them as subtraction, but it's just sort of the easy way to think about it. But the way that we actually define this is as an equivalence class. Equivalence classes, if you have never encountered them before, are sort of sets of numbers where they're almost like bins of numbers where the elements inside that bin they all equal in some way, or they represent the same value. So for me, you can think of equivalence classes with fractions, that 1/2, 2/4, and so on. Those all represent the same number. So you can say they're all a part of the same equivalence class, okay? So we're basically doing the same thing for the integers here. So that for us, 3, 2 would be in the same equivalence class as 2, 1, and 1, 0, and so on, okay? Any pair where 3 minus 2 equals 1, any pair where the difference is 1, they're going to be in the same equivalence class. So the way that we define this, though, is we can't use subtraction. So the way that we do this is we say that a comma b is in the same equivalence class as c comma d if and only if a plus d equals b plus c. Okay, and you can see that here that would be true, right? 4 plus 4, 2 plus 2, and so on. So if a plus d equals b plus c, then they represent the same integer. So we'll denote such an equivalence class as with square brackets. So it would be square brackets a comma b. So this is the integer, and then this means the equivalence class. So it's this pair and also every pair that has this relationship. So that's it. The set of all pairs of natural numbers in this form, we'll call it the integers, and we'll denote it by a z. So now with this in hand, we can define addition of integers and multiplication of integers without having to resort to plus and minus, 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 and so on. So we can define, so this is the addition in integers of the integer a comma b and the integer c comma d equals a plus c minus b plus d, which equals a plus c comma b plus d, right? Because an integer is one natural number minus another one, right? So this is another way of writing the subtraction there. So we're actually defining, this isn't actually part of the definition. We're defining addition of two integers to be this number. But you can just see that it's true because if you take the first two minus the second two, then it equals that. Just to show you that this would be a minus b plus c minus d equals a plus c minus b minus d, or minus b plus d, right? So again, we can't actually use minus because we're only in natural numbers, which causes problems if the second number is bigger than the first. But you can just see that this is true, so that this is the same as this. So this is the definition of addition. And again, I know that this is all odd, but the reason we're doing this is we need to define the integers in a way that we can embed them into our two sets of real numbers, x and y. And right now, all we have so far to work with are the natural numbers. So we have to do something to extend our natural numbers into the realm of negatives as well. So we have to do something to define what we mean by the additive inverse of a natural number and what number we mean by that. That's what all this is for. Once we've done this and we've demonstrated that we can embed these into the real numbers and that there's an isomorphism between them, then we'll know we've shown that they exist. So after that, we'll be able to use our more natural symbols for minus, for subtraction, and so on. Okay. So multiplication is defined as okay, so this is the definition of multiplication. And again, we can justify this easily. So this is a minus b times c minus d, which equals ac. First, minus bc minus ad plus bd. So rearrange them, we have AC plus BD minus, take out a minus, and we have BC plus AD, and then a minus, you can just rewrite that as AC plus BD, comma, BC plus AD. And that's what we have with rearranged. Okay, so one more thing, negation, or the additive inverse, is obtained by simply switching the order of the numbers. Right? That's easy to see. If this is 4 minus 3, that's 3 minus 4. That would be 1. That would be negative 1. So that's it. As for ordering, AB is less than CD if and only if A plus D is less than B plus C. Again, we can see that easily if we just let ourselves use the minus for a second. A minus B is less than C minus D. That means we can move the D over here and move the B over here. So that implies that A plus D is less than C or B plus C. Right? We add B to both sides, B plus C. And then that's what we have here. Okay. So just to say it one more time, remember, even though when we're justifying this, we're looking at minuses, but we can't actually subtract B from A in the natural numbers, because if B is bigger than A, this would be negative, which doesn't exist in the natural numbers. But what we're doing here is just justifying the definition. This is a definition. This is a definition. Multiplication is a definition, and the addition is a definition. We're setting this times this means this, and this less than this means that a plus d is less than b plus c, because this is all in the naturals. This is all in the naturals. So this ordering works. So that means that here, one of these might be a, quote, negative number if b is bigger than a, but we can still see that ab is less than cd if a plus d is less than b plus c. Okay, one last thing to point out, every number in every one of these, every equivalence class has a unique member in the form of either n comma 0 or 0 comma n. So the natural numbers are identified with n comma 0, right? So 1, 2, 3, it's just 1 minus 0, 2 minus 0, 3 minus 0, and so on. And then the negative numbers are associated with a natural number, 0 minus some natural number. So then these would be the negative numbers, these would be the positive numbers, and then 0 would be 0 comma 0. And notice, to get comfortable with these equivalence classes, this is not an equivalence class. This is a member of the equivalence class. So what I'm saying is each equivalence class has a unique member that is n comma 0. So what that means is that each natural number is associated with only one equivalence class, and each negative number is associated with only one equivalence class. But these are just members of the equivalence class. So the negative numbers are denoted by minus n. Okay, that's integers. So we've defined integers now. Now we have to embed them into x and y. So embedding into x and y. So for all a comma b elements of n, now we can say, or equivalently, the embedding of the integers into x will be defined as, so e to the x, or e sub x. Okay. What are all these parentheses? So e is a function. This means it's an equivalence class. This is a member of that equivalence class with a and b as the members. So we're taking this equivalence class and we're sending it to a number in x. The number that we're sending it to is, this is a natural number. So this is the natural number a embedded into x using our embedding from the natural numbers, plus the natural number b embedded into x. We're taking the additive inverse of that and we're adding those two numbers, a embedded in x plus the inverse of b embedded in x. We know that the inverse of b exists already in x because x has the addition axioms for a field. And one of the addition axioms is that for every letter a in x, there exists a b in x such that a plus b equals 0, right? So this number has an inverse in x, even though b in the natural numbers doesn't have an inverse. Now, you might ask yourself, am I right? Am I wrong? If the negative numbers already exist in x, why are we going through all this trouble with the natural numbers and constructing the integers in this way? We already know that if we've identified b in x, then the inverse of x of b also has to be in x. But the point here is that with x and y, even though we know that x and y both satisfy the addition axioms and the multiplication axioms and the ordering axioms, we don't actually know anything about these numbers. All we know is that there's an element named 0 and that there's another element named 1. Now we know, in addition to that, that if you take 0 and you add 1 to it, you get 1. If you add another, you get what we call 2. If you add another, we get what you call 3. But right now, all the axioms tell us is that for every natural number, b, there is an additive inverse. but we don't have any idea where it is or what it is. Is it close by? Is it an equal distance? We don't know anything about it. Maybe these numbers are ordered 0, comma, -1, 1, -2, 2, etc. Or maybe it's 0, 1, 2, 3, and over here it's -1, -2, -3, and then here it's -6. Maybe it's every 3, right? We don't know. We don't know yet. And in fact, that's what we're doing right now, because we don't know what the inside of x and y look like. So what we're doing is we're constructing these integers. We now have integers that work in the way that we know that integers do. But now the integers exist, but they're not yet inside x and y. So although we have some sense of what the integers do, we don't know that that's how they are inside x and y. That's why we have to embed them in x and y. Then we have to define the isomorphism to
do Boone work. That's right. Yeah. There's an example from the village rolls in 1313
to demonstrate that in fact they're in both sets in the same way. So first we have to actually put what we just constructed into x and y, because it might be this or this. But what we're going to show is that by embedding them in this way, we're going to be creating the order that we intend, where it's 0, 1, 2, 3, and -1, -2. Whoops, keep doing that. -3. Okay, that's what this embedding does, and then the isomorphism will show us, that mapping will show us that they're the same in both x and y. So this is another example where it's easy to think that it's all obvious, but it's only obvious because we're so comfortable with it and we've been learning it in this way since we were 5. We don't actually know the stuff that we think we know yet. That's what we're proving right now. So just starting with those logical concepts from piano, we made the natural numbers and now we've used them to define negatives and so on. So, okay, this is the embedding in x. It's the equivalent for y. Right, okay, that's y, that's x. Now we have our new set of integers embedded into x and y. Now we have to show that in fact they're put into x and y in the same way. There's no folding or twisting. We're nailing them down in the same way, one right on top of the other. So we'll call the set of integers embedded into x, z of x, and the set of integers embedded into y, z of y. Okay, so one last thing. There's a lot of different ways of writing down what we're talking about here. So just to put them all down, an integer in zx can be denoted. All of the following are equivalent. The point of this is just to show you that there's a lot of ways of talking about the same thing. The good news is, so m and n are still natural numbers. Oh, I'm sorry, I needed to start with let m equal e to the a. So we can either use m and n, or we can obviously write the same thing using the embeddings of two natural numbers. Or we can talk about this by making the integer first and then embedding into x, or we can embed the two natural numbers and then take the equivalence class to make the integer, which is what this is too. So they're all equivalent. And the same goes for z of y. Okay, now the isomorphism. So let m and n be elements of the naturals in x, which means, again, that m equals the embedding of some natural number into x, and n equals the embedding of some natural number into x, where a and b are elements of the naturals. Or we can just talk about the naturals inside, or that we can talk about m and n inside the naturals inside x. Just remember that that means that we're actually embedding them the way we did in the last step. So that means that m comma n is an integer in x, embedded in x. So we extend 5n to a new map, 5z, by setting 5z, 5n, 5n of the integer m comma n So what did we do here? This is the new map, which takes one of these new integers as input, and it gives us an equivalence class in Y using only our mapping of the natural numbers. So what we did is, yet again, we're going down, over, and then back up. So we want to be able, we're defining an isomorphism from X to Y of the integers. In order to do that, we have to take it back a step to what we already know, which is the isomorphism of the natural numbers. So we're associating the new map, we're showing how to define it in terms of the old map. So we need to show that that phi of z, that this map is an isomorphism from zx to zy. Okay, so first we have to show that phi of z is well-defined. Remember, the first thing we have to do is show that this is well-defined and onto and one-to-one. And they're not so easy for this because the integers are equivalence classes. So we need to verify that this is well-defined, which means that if k, l, m, and n, elements of n in x, we need to verify that if kl equals mn, then phi of kl equals phi of km, right? And this is the vertical test. What this means is that if the x is the same, then the y is going to be the same, that it doesn't go back like this. So there's not multiple values of y. So what we're showing is that if the inputs are the same, then the outputs are going to be equal as well. Okay, let's start on a new page. So we start with k comma l equals m comma n. That implies that k minus l equals m minus n. These are in x's. That's just the definition. That implies that we can rearrange them now. So k plus n equals l plus m. We're still in x. That implies. Now, we already know that phi of n is well defined, which means that if k plus n equals l plus m, then phi n of k plus n equals phi n of l plus m. Now we know as well, because we just verified that phi of n is an isomorphism, that means that it preserves the additivity, so we know that n of k plus n of n, phi of n equals phi n of l plus phi n of m. That implies, now we can rearrange it again, so we can move the l back, move the n back, and we get phi of n k minus phi n l equals phi n m minus phi n n, right? So we move this one over there, this one over there. Now we're back where we were. Now this again, we can just use the definition of integer to rewrite this as equivalence class of phi n of k, phi n of l equals phi n of m, phi n of n. And then this is the definition of our map of z. Right? This is the definition of the new phi. That if you take phi of an integer, you get the equivalence class of the phi of k minus and the phi of l. So m and n, m and n. So we did it. We started with k comma l equals m comma n, and we ended up that phi of k comma l equals phi of m comma n. Good. So it's well defined. Now we need 1 to 1. 1 to 1 means that if f of x equals f of y, that implies that x equals y. So suppose that phi z of kl equals phi z of mn. So we've got to show that kl equals mn. So the definition of this means that phi n of k minus phi n of l equals phi n of m minus phi n of n. That's just the definition of phi of zeta, or phi z. So we're doing almost the same thing we did just before. So if this is true, then we can rearrange these and get phi n of k plus phi n of n equals phi n of l plus phi n of m. That means that phi n of k plus l equals phi n, of k plus n equals phi k of L plus m. Now, since phi sub n is 1 to 1, if phi of k plus n equals phi of L plus m, that means that k plus n equals L plus m. Then we can rearrange these again. That means that k minus L equals m minus n. This is the definition of k comma L equals m comma n, right? That's just the definition. So that proved it, because we needed to show that if f of x equals f of y, then x equals y. So we had phi z of kl equals phi z of mn, and we concluded that kl equals mn. That's it. Onto means that for every y in the range or the codomain, there exists an x such that f of x equals y. So it means that all of the range is covered, right? It doesn't like level out somewhere. All of the y's are covered. So we have to show that given some value in y, there's going to be a value in x such that phi z of that number equals y, the number in y. Okay, so we know that phi of n is onto. So that means that for every mn in the integers in y, with m and n in the naturals in y, right? That should be obvious, but just to make it clear. There exists a kl in n in x such that phi of n of k equals m and phi of n of l equals n. So what I'm saying here is that because the natural numbers, the phi of the natural numbers is onto, then for every one of these pairs of numbers in y, so we have an m and an n in the naturals. For every m and n in the naturals, there's going to be a k and an l in x such that there's a phi from k to m and a phi from l to n. So then with those kl, then k comma l is an element of zx such that phi z of that integer equals, right? This is the definition of z, equals, and this just equals m and that equals n. So, and that's what we needed to prove, right? So we started with an m and an n in the integers in y. So that means that m and n are the naturals in y. That means that we know that there's a k and an l in the naturals in x that are mapped to m and n. So that means that the k and the l as an integer in x, if we take the map of the kl, it equals the mn. That's what we needed to show. That for any mn in y, there is a kl such that the map goes to mn. Okay, so we've shown that phi of z is well defined, 1 to 1, and onto. So now what we have to show is still that phi of z is an isomorphism. So addition. The cool thing is that now we had to use an induction for the natural numbers. We don't need to use induction anymore because we've already shown the first set. Now we're just building off of that set. So let k, l, m, n be elements of the natural numbers in x. So kl and mn are both elements of the integers in x. We need to show that phi of kl plus mn equals the phi of the first plus phi of the second. Okay, so this is the same thing we did before. We have to show that if you add them in x and then apply the map, you can also apply the map first and then add them together. So this is in x, that's in y. Okay, I think I can do it here. Actually, so let's not do it. Okay, let's switch to the next page. So we start with phi of z, kl plus mn, right? So the addition is inside the parentheses. So we're taking the map of this whole thing, the kl plus mn equals. So we'll just take the definition of the addition of integers, still inside the parentheses. So it's k plus m, comma n plus x, or l plus n, right? This is just the definition of addition in integers. Now we just take the definition of our map. So we're going down to the naturals and then over and then back up. So this equals phi of the first one, phi of the second one. So it's just phi of the first one, phi of the second one. Now we know that phi sub n preserves addition. So now we can expand this So it equals 5nk plus 5nm, comma, 5nl plus 5nn. So that's just the additive property of 5n. Now, we're going to use the definition of integer addition again in the opposite direction. So if we have k plus n and l plus n, that equals kl plus mn. So, but now we're in 5n. So we go 5k, 5l plus. So this was the definition of addition of two integers. Now we just apply the definition of 5z, because here we have it in n and we're rearranging it to z. So this is phi of k comma l plus phi of z. That's what we needed. We started with kl plus mn in x, and we just showed that that's taking the phi of that is the same as taking the phi of kl and adding it to the phi of mn. That's addition, multiplication. So again, let k, l, m, n be elements of nx. So kl and mn are elements of integers in x. So now we need to show that if we multiply first and then take the phi, so we multiply first and then map it to y, that equals mapping them first and then multiplying. Okay, so first you multiply, then you take the map, that equals mapping them first and then multiplying. This actually takes a couple more steps than the other, so let's go to the next page. So, but again, we start with doing the multiplication in x. Apply the definition of multiplication for integers in x. Now we apply the definition of phi of zeta. That's the definition of our new map. Now we're going to just expand this a little bit. So first we're going to use the additive property of the natural map. So this equals km plus ln, phi n of km plus phi n of ln, comma, and then phi n kn plus phi n of lm. Right? This is just the additive property. They were inside, we took them outside. Now we're going to do the same thing using the multiplicative property of phi n. So this one gets long. So we separate these out. So we have phi n of k times phi n of m plus phi n of l times phi n of n, comma. Same thing for this one. Phi n of k times phi n of n plus phi n of l times phi n of m. Okay, so this is the first element, this is the second element. We're just talking about this thing, but we just applied the additive property to separate them and the multiplicative property to separate them. So we have this times this, plus this times this, and so on. Okay, now we're gonna start recombining them. Because what we have here now, these are all in y. This is k in y, m in y, l and n, both in y. So we have in y, k times m plus l times n, comma, k times n plus l times m. That's just the definition of integer multiplication in y. So now we can simplify that. So this is just the definition of multiplication of two numbers in y. Wait, I think I got these. Oh, yeah, I got these wrong. Let me do this again. Equals. We're going to end up with two integers. We're multiplying two integers. So we have the first one is phi n of k, phi n of l times in y, phi n of m, comma, phi n of n, right? The definition of multiplication is complicated because it's km plus ln is the first number, and then kn plus lm is the second number. So this equals this number times this number, all in y. Now these are all n's. Now we can apply the definition of our new map. So we have that phi of z, so that's this one, times phi of z And that's it. This is the definition of phi z, so KL. This is the definition of phi z, mn. That's it. So we proved that if you multiply KL times mn in x and map it to y, it equals the same thing as mapping KL to y, mapping mn to y, and then multiplying those two together. Those two things are equal. That's what we needed to show. Finally, ordering. Let's go to the next page again. Ordering. Okay, we need to show that if k comma l is less than m comma n, that implies that phi k comma l is less than phi of m comma n. Okay, so again, start with the first. So again, so k, l, m, and n are all natural numbers in n, same as before. So we have k comma l is less than m comma n. That implies, so just take the definition of these. We have k minus l is less than m minus n. So now we can just rearrange these. We can add L to both sides without changing the inequality. We can add N to both sides without changing the inequality, and we end up with K plus N is less than L plus M. Now, because phi sub N is order preserving, that means that if this is less than this, then phi of N of K plus N is less than phi of N of L plus M. Now we're in Y. Now we can apply the additive property of phi sub n. So we have K plus phi n is less than phi of L plus phi of M. Now we can rearrange them once again the way we just did. So we can, preserving the order, we can subtract L from both sides, subtract N from both sides, and we get that phi n k minus phi n of L is less than phi n of M minus phi n of n. Now we just apply the definition of an integer, and we have that this equals phi n of k comma phi n of L is less than phi n of M phi n of n. This is the definition of our new map, phi of z. So this, we can just rewrite this as phi of z of KL is less than phi of z of m n. And that was what we wanted to show. We started with KL is less than mn, and we showed that in that case, phi z of KL is less than phi z of mn. Okay, that's what we needed to show. Phi z preserves addition, phi z preserves multiplication, and phi z preserves ordering. That's what we needed to show. So phi z is an isomorphism, which means now we've nailed down all of the integers, the naturals and the integers. So next step, we'll do rational numbers. One of the most interesting things about this step to me is how similar the integers are to the rational numbers. So the next step of the proof, we're going to have to define rational numbers, which is very similar to this, then go through again to prove that phi of q is an isomorphism. Then comes the toughest part of all, which is proving the real numbers also have an isomorphism between them. So come back.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.